In the past 9 months or so, I sort of took a little bit of a detour from the work I've been doing with Presto and Gluten projects to help accelerate analytics engine, and went to learn about how AI data loading works. As Pedro was explaining, AI training became the biggest consumer of the data in the warehouses. And so understanding how that data is being read, transformed, and feed into training became interesting and important. And one of the questions I was looking to answer is, what's so different about preparing data for training? How is it different from the work we're doing in Presto, in Spark, to prepare dashboards, to prepare reports, to answer questions about the data, finding insights and about the data? Is it the same? And if so, why we need separate systems to do this data loading for AI? And so hopefully today I'll share some of the learnings, some of the findings. In summary, it turns out that data loading for AI is very similar to what we do in Spark, what we do in Presto, but it has its unique differences. You need the nuances which matter and that require new capabilities, new features, new optimizations. In Meta, we use primarily two systems for analytics, which is Presto. Today it's largely Prestissima, and Spark. And today it's moving into Gluten, into PySpark, into more optimized versions. And for AI, we're using a third system, and we call it DPP. If you look at it, it looks very similar to both Presto and Spark. It essentially runs a two-stage query. First stage, essentially table scan, kind of reading from storage, doing basic transformations, think about filter, project operators. It runs on a tier of CPU machines. And then those machines prepare data and put them into output buffers, from which it's being fed into another tier, the second tier, which runs on GPU machines, which reads data from CPU tier and feeds into training processes. One way to think about it could be like we're running an aggregation, where aggregation operator is essentially an AI training. It keeps consuming data, you feed data into it, accumulates the data, and at the end gives you a model. In a way similar how in aggregation in a traditional engine works. It keeps accumulating data, keeps summarizing, it keeps accumulating, and at the end gives you, say, a number of distinct values in your input. The shuffle, the data exchange between those two tiers is a bit different. In Presto or Spark, usually we do like a hash-based shuffle, where we move the records that hash the same way to the same machines. But here, there is no affinity between the data coming out of CPU machines and going into the GPU, so we call it like arbitrary exchange. Essentially, any trainer can pull data from any CPU node, and it's first come, first serve. So you prepare the data, it can go into any training machine, and as long as the training machine is ready to get more data, it will pull that data. The nuances about that, like for example, this arbitrary exchange, it actually exists in Presto. And it's used when we are implementing table writer. In certain cases, it doesn't matter which nodes would write the files. And so there is an arbitrary exchange in Presto. So we can say that this is kind of similar. But the differences come when we realize that trainer processes specifically care about the size of the batches. They really like homogeneous batches, say batches of 1024 rows or batches of 512 rows. There is a certain batch size that they advertise, and they really like batches of the same size. That's essentially because they run on GPUs, and if you give the same size batches which are processed the same way, that processing happens faster. And therefore, the data produced by CPU machines needs to come in batches of specific size. And that's a functionality that doesn't exist either in Presto or in Spark. It's called a rebatcher process, where we take batches which are coming out of table scan or filter operation or project operation, and we stitch them together into batches of a fixed number of rows. Another important property that AI requires is that the order of the data produced by the CPU tier matters. In Presto or Spark, it only matters the total set of rows that's being produced, and very rarely we have like an order by operator at the end, usually for very small data sets. Definitely not when we're processing billions of rows. We would not put an order by on that. But in training, different models have different requirements, and often they want data either random, which is also like a property of the data. You can't just read it anyway and pretend it's random. You actually need to shuffle the data. Or sometimes they want data in actually chronological order, like older data comes before newer data. And if you think about the amount of data being fed into training, sorting it, just how we do it with a traditional order by operator, is not practical, simply cannot possibly work. And so the sorting implementation in AI training is implemented by sorting splits. Essentially, you think about your data is usually organized into partitions. Those partitions could be daily partitions, hourly partitions. They could have a few more partition keys, but they have this temporal component to it. And so you can sort the splits. You can sort the splits by day partition and hourly partition, and then sort the files or chunks of data within those partitions randomly, and that gives you the ordered or like nearly ordered data, which is essentially good enough for training. One other aspect with data reading for AI is that imperfect data or not 100% correct or not 100% exactly ordered is usually okay. And that's not the case with any sort of analytic engine where correctness of the execution is the top most important feature. We never say that Presto query can return almost correct results or return almost all the rows except few rows got lost, or maybe like they got a little bit corrupted. This is just never okay, never works, but for AI that works. And so we'll see further on, like here we're talking about that how sortedness can be close enough or good enough, which allows us to implement it practically and efficiently. But we'll see how also like dropping some rows to provide fault tolerance is also okay. One thing that trainers do not tolerate, and that becomes important focus for building the engine for training, is duplicate data is death. You can lose a row, you can lose maybe some small percentage of rows, not deliver them, but it's really disastrous if you start feeding the same data again and again to the trainer. Even a little bit of data duplication is a major challenge, and models simply can't tolerate that. And so one thing that we'll start seeing is that for many of the features that are required by training, there is no SQL way to describe the property. Like there is no way to describe this kind of order that's not strict order by, or there is no way to efficiently describe that I want it kind of sorted chronologically and then within big chunks, say hours or days, I want data shuffled. And so one of the things we as a community need to think about is how we evolve not only the engine and the implementation, but how we evolve the language which we can use to specify the data reading. One other requirement that training has to do about union. In training, like Pedro was mentioning, we cannot starve GPUs. And therefore, most operations, if essentially all operations, have to be somewhat streaming. We cannot, like, for example, use a hash join because it takes some time to build the hash table. And while you're building it, you cannot produce results, which means GPUs are sitting, waiting, idling. And so the algorithms are usually streaming aggregation, merge join, and like for union, it means there is no union, there is only union all. Because if you need to dedupe something, that becomes a bottleneck. It becomes too slow, too hard to implement with so much data. So, but union all is a common construct in training for AI, where you have training data from multiple places and you want to combine them. And now, union all semantics in SQL just says, okay, make sure that in my final data set, we have rows from all the branches of the union. But that's not good enough for training. Usually training wants each batch coming out of the data processing pipeline to have a mix of data from all the union branches. So it's almost, you can think of like if you're, there is like online training and offline training. If you're doing online training and the data is coming from 3 different places, you naturally get like a mix of data and you train on that mix of data. So when you're training offline on like data stored in Hive, you want to emulate that kind of data shape. You don't want having one batch of data coming from one source and having one characteristic to it and having your model learn the pattern in that data and then abruptly switch to another source of data from another union branch, which has different characteristics, different patterns, and now your model keeps going back and forth, and that creates not very good results. So what you want just this kind of nice mix of data from all sources with all patterns present pretty much in every batch, or at least nearly every batch. And not only you want a mix, but you want the ratio of data from different sources to roughly match relative sizes of those sources. So if you're like combining data from 3 sources which are substantially different sizes, you want the mix in each batch to reflect the size ratio of those sources. And just like the previous examples, here we don't even have a language to express that using SQL or any known SQL extension. And that's like a challenge for us as a community to figure out how to start evolving SQL to be able to express those kind of data properties in a convenient way. So here I just kind of have an example of that kind of union. And in addition to the mix of data coming from those branches, the order in which the data comes from is also a little bit interesting. It could be that you have multiple data sources and then you say, I want a mix of data in every branch, and then I want my data coming roughly ordered, older first, newer next, and kind of like at a granularity of, say, like daily partitions or hourly partitions. And so I want like Monday, then followed by Tuesday data, followed by Wednesday data. And that's all fine. We can do all that. But then sometimes what you have is you have two sources or you have multiple sources. And logically, Monday's data for one source corresponds to Wednesday data from another source. So you can have like some data that like logs activity that happened on Monday, and then you wait for some events to happen a few days later, and then you want to combine an action that happened on Monday with an event that happened on Wednesday and train your model on that kind of data. And so in this case, you have like a somewhat like a logical partitions, which say that Monday's data in source 1 corresponds to Wednesday data in source 2. And the way you can express it is by having a transformation on top of partition key, like a DS partition key in one source. We use a UDF called DS shift. Essentially, DS shift means add so many days to the date. So DS shift, DS6 means if DS is Monday, then DS should add 6 days to it and arrive on Sunday, I think. Sometimes it's hard to get those off by one things right. And so that presents like a new challenges to split generation and kind of figuring out what are the actual partitions, logical partitions for that query, and how they map to actual physical partitions. And again, that's an example of what's important for AI training and what simply doesn't exist in traditional analytics world. Here I'm just giving more examples about like how this DS shift operation allows us to implement the logical partitions. The key is that being able to solve the equation DS shift DS6 equals some constant value, because you need to be able to go from a logical partition to an underlying physical partition, and that means solving those kind of equations. And you can do that as long as you're using invertible UDFs, functions that for a given function, you have another function that if applied twice, you get an identity. And DS shift is, of course, that, like DS plus 6, you can take a result and minus 6 to get the original value. Which essentially means that the optimizer, like the language, needs to evolve to allow us express those properties, and then the optimizer needs to become more powerful as all of a sudden now it needs to be able to solve those equations that involve invertible functions, specifically for being able to push down filters all the way to table scan and translate them to metadata queries rather than filter operations during runtime. And so we're seeing how the language needs to evolve, how the optimizer needs to support the new language, and of course execution needs to support both the optimizer new plans and new language. Just to summarize, the GPU starvation is the most important concern in AI training. When we talk about efficiency, primarily we're talking about how many CPU machines we need to keep one GPU not starved. Like the fewer CPU machines we need, the more efficient we are, which effectively means that we're not looking for, say, CPU savings. We're not looking at like CPU utilization and trying to squeeze a 5% here, 5% there. We're not looking at like memory usage. We are looking holistically at literally like number of machines you need to support one GPU. And the fewer machines, the better. At the same time, if the optimization doesn't allow to reduce the number of machines, maybe you optimize and now all the machines use less CPU, but the throughput, the number of batches they produce per minute hasn't changed much, then it's as if that optimization didn't happen. And streaming algorithms are essentially the only ones that are practical. And that's why we'll be seeing more focus on those, like streaming aggregation. And recently, Jamie from Velox team has been improving the efficiency of that particular operation. And that was really helpful, like 3x improvement in batches in total throughput, not just CPU time. Merge join, just by nature, is a streaming algorithm, so that's used quite widely, and the newly added index lookup join becomes relevant and important for AI training. Another kind of aspect with training jobs is that they take a long time. Like a long time meaning sometimes they take days, some of them take weeks. Which means fault tolerance and being able to fail and not forget all the work that's been done, but rather pick up from where you left, or maybe a little bit behind, redo a little bit of work, but not all the work, is becoming critical. And so tolerating failures of individual CPU nodes without failing the whole job, and also tolerating just like fatal crashes or fatal conditions and still be able to resume from some reasonable state where most of the work is preserved becomes critical. And fault tolerance is just plain hard, especially in distributed systems. You need to apply some sort of trade-offs. For AI, what helps is that losing some data is okay. Duplicating data is not. And therefore, the system that's feeding trainers is being designed to deliver at most once semantics. It essentially guarantees that a row will never be duplicated, will never appear twice, but it also says there can be some data loss, especially in the face of failures. And so it's important to have that semantic, and in addition to have some sort of control on, like some sort of tracking of how much data is being lost or potentially being lost, so that at some point you do need to fail the job. Like if you're losing more than certain amount of tolerable percentage of rows, it's actually better to fail and say something is catastrophically wrong rather than spending more time, more days training and then just getting a wrong model that succeeds in training but then fails, then is deployed in production. And so the system we use, the DPP system, has some logic where it allows for checkpointing progress. And it allows to pause a job and then resume it from that checkpoint. And that not only kind of supports fault tolerance, but it also supports this use case where scarce GPU resources, if they are used, for example, right now to train a medium importance job, and a higher importance job is waiting access to those GPUs, we can pause the job that's running now, let the high priority job go, and then it finishes and GPU resources become available again. The job that was paused can resume, it will continue running without losing the work that it's done. And so that's currently being implemented as with certain assumptions in mind that allow for somewhat clever and relatively simple technique that doesn't require a lot of development, doesn't require a lot of kind of complication that's traditionally involved in implementing checkpointing to be viable. One assumption is that the query plan or the data frame that's being used in real life is deterministic. And like many things AI, it doesn't need to be 100% deterministic. It needs to be deterministic enough. And here, what it means is that Individual values in individual rows can be slightly different when ran again, but the set of rows needs to be the same. Like the number of rows produced needs to be the same. The order in which they are coming out of like individual threads of execution need to be the same. And so here I have like an example where we have a table scan followed by filter and followed by project. And the project uses rand, which of course makes it non-deterministic. But that's okay, because project doesn't change the cardinality, doesn't change the order of the rows. And for the purposes of checkpointing, that's fine. However, if the rand is used in a filter, that presents a problem. If filter is non-deterministic and then you rerun again, you run a risk of having duplicate data because the rows are just not comparable to each other. And so the way checkpointing works in AI is that we are processing the query one split at a time. And for every split, each split is running single-threaded. And single-threaded and somewhat deterministic, so it produces a stream of output rows. And we can number those rows. As they're coming out, they are saying, okay, row 0, 1, 2, 3, 4. We create batches from those rows, and for each batch, we annotate it with metadata. We know that this batch was produced by a certain split, and we know that this batch contains a range of output rows from the output split, from the output stream corresponding to that split. Which means if we need to produce it again, all we need to do is take the same split, run it through the same query, and wait for the row number at the start of the range to get the batch. This very simple technique that essentially allows us to annotate output batches and track which batches were fed to trainers, to GPU processes, and on restart, rerun the splits which didn't have all their batches processed by trainers, and then splits which were not processed at all, works remarkably well. It does have those assumptions. It takes a little bit of time to understand how this tracking of output rows works, because it's not tracking the input rows, which is something that's pretty straightforward to think about. Like you would think about, okay, I need to track which rows I've read from storage. And that doesn't work because all the filters, the joins, and other conditions. But tracking output rows surprisingly works. And again, that kind of checkpointing logic today exists only in DPP, only in the AI training data loading system. It doesn't exist in Presto, doesn't exist in Spark. We do not have native support for that in Velox. But that's something we need to look into and figure out how to add. So similar mechanism that's used for checkpointing is used for also fault tolerance. Then a machine, one of the CPU machine goes down, the coordinator or the master node remembers which splits were assigned to that machine. It also knows which batches from those splits were delivered to trainers. And so it can make the splits which were not fully processed, not fully delivered to the trainers, available to other CPU nodes for pickup and reprocessing. So fault tolerance, so we talked about data ordering, we talked about mixing data in batches, and we talked about the fault tolerance. Another big aspect of reading data for AI is handling enormous sizes of the maps that are storing features. As Pedro was explaining, there are like thousands, sometimes dozens of thousands of features stored in a single column, in a single map column. And many of those are experimental. Some of them are used for one model training, some are used for another, some are not used at all because the experiment didn't pan out and cleaning that up was not a priority. And so in general, what we are seeing that in individual data reading for a specific model training job reads about 10% of keys from any given map. And when we're talking about those huge maps, reading only a tenth of it versus reading the whole map is a big difference. And it's a big difference not only because it takes CPU time, it takes network bandwidth to transfer that data, to kind of copy, to decode it, but one also important aspect is it takes a lot of memory to simply store it on the CPU machine. So if you're storing 10x more data than needed for processing, essentially it means 10x memory is being not used. And interestingly enough, while Presto and Spark tend to be CPU bound, and that's why we mostly primarily talk about CPU usage. We saw a slide that Pedro had about the distribution of CPU time across different operators. It's very relevant in the world of analytics. What's relevant in the world of AI is how much memory we need to run a single thread processing for a query. It turns out that data reading for AI is memory bound, and CPU is plentiful. There is usually about 30-ish% CPU utilization on the CPU machines, but they are booked in terms of their memory usage. There is CPU to create more threads and go faster, but there is no memory to do that. And so figuring out why there is no more memory, why we're so CPU memory bound, becomes critical to understanding how to make AI training go faster or use machines more effectively. The figuring out how to not store large maps in memory when only 10% of them is needed makes a big difference for memory usage. And so if we solve that problem, if we don't read the whole map, but only read the keys that we need and do that in memory efficient way, for example, without having to decompress and decode the map, which still takes memory, allows us to not change anything about the CPU efficiency of the process. It simply allows us to add more threads and go faster. And that's why like the feature projection or like which refers to reading only certain keys of a map is very important. I have this kind of snippet from just one kind of node from a query plan from one of the queries that's used in AI training. And the reason I have it here is simply to kind of illustrate the sheer scale and the difference between query plans in analytics and query plans in AI. Like we all probably know in production, queries are huge. Query plans are huge, sometimes hard to read, a lot of things in them. But we still have all the systems provide explain command, which gives you a whole plan, full plan, no abbreviations. This doesn't work for AI training jobs. When I started working in that space, I was kind of looking, okay, so what are we doing? What are we reading? Where's the plan? And I printed the plan, and it kept printing and printing and printing in my screen, and I was seeing kind of numbers and letters and more numbers and letters, and I'm like, what is this? It's so big, you can't, like a human cannot even tell how many plan nodes there are, or what are they. And so the first thing we did is created a summary of a query plan. Essentially how, like in big data, when we have large data sets, data scientists came up with ways to summarize those. Like they came up with things like average, percentiles, min, max, which gives you a few numbers, which give a sense of what kind of data you have, but it's not the data. There are not enough details there, but you can work with that. So we did something similar for query plans for AI. We created a summary. And essentially here, we don't give you the full plan, but we do tell you, okay, there is a project operator. And we tell you how many output columns it projects. So here we say 14 fields, meaning 14 columns being projected out of this operator. And then we give some names, but not all, because 14 is small. Sometimes it's hundreds and thousands. And we give a name and a type. But if you look at that type, row 1, 3, 4, 6, 9, looks like some sort of ID maybe, some sort of lookup thing. What this is the number of fields in that struct. And it's not a typo. I didn't type it by hand. It's like a screenshot. And I didn't look for the most biggest plan I could find. It was just the first one that was lying around on my machine. 13,000 fields in that struct. And then if you look at how they're computed, we're not going to produce expressions which are many pages long. So what we do, we have a summary of what kind of expressions are used in that project. So we're saying there is a 34,000 function calls, UDF calls. There is 42,000 constant values being used in those function calls. So you can think of something like a plus 1 plus is a function call and 1 is a constant. And there's it accesses 17,000 columns, or it accesses them that many times as a field expression. And then we provide a list of functions with the count of each function, how many each function is being used. And so we can see bucketize is being used almost 4,000 times. And some others are used not so many, or I think that just got cut off. So I'm just providing this to show that the scale in AI applies not only to data, but to metadata, and to simply the query plan that's impossible to even just print out as is. And so later, I think it will be probably next, tomorrow, I think Ori will be talking more about how we can efficiently process plans like this. Because one intuition we get from it is, okay, if there are so many subcolumns we are processing, we probably are not doing data-dependent operations across all of them. So there might be an opportunity for us to break it down into data-independent subsets and run those in parallel, as opposed to traditional project operator, which runs serially. And so we'll learn more about it, hopefully tomorrow. And that's essentially where we are thinking we can solve the memory problem. If we can parallelize the single-threaded today query execution by breaking down expressions into groups of data-independent operations, we can run more CPU, use more CPU to do more processing within the same memory envelope. And so we keep the memory usage. I'm being told I'm going over time, so I will wrap up. I think what I'll say is just thank you for being here. Thank you for being part of Velox community. Thank you for helping us build Prostissima and Gluten. I think we'll hear today from Amit and others on how successful those systems became. That's something that when we started, and we were telling people that Presto can run 3 times faster. And it was like, what? Do you know what you're talking about? This is a reality. And this is a reality, and I can't be more excited about this. As Ali and Sridhar were saying, today and tomorrow is celebration time. I'm celebrating with you. Thank you for you all coming to celebrate with us. Thank you for coming as a community. And let's chat more during happy hour.